Every day, the world consumes around 100 million barrels of oil. That number is almost hard to even picture. But when you think about what oil actually powers, cars, planes, cargo ships, factories, farms, and entire economies, you start to realize just how deeply modern life depends on it. And here's the contradiction. The resource that keeps civilization running is hidden miles beneath the earth, trapped under rock, pressure, and darkness. And getting to it takes giant machines, extreme precision, and industrial systems so complex that a single mistake can cost millions. So how do we actually find oil? How do we drill for it? And how does that thick black liquid end up becoming gasoline, plastic, jet fuel, and countless everyday products? That's what we're breaking down today. Most people grow up hearing that oil comes from dead dinosaurs. Sorry to kill the Jurassic Park version, but it's mostly wrong. Crude oil mainly comes from tiny marine organisms and algae that lived hundreds of millions of years ago. When they died, they sank to the sea floor and were gradually buried under layers of mud and sediment. Over huge spans of time, heat and pressure transformed that buried organic material into hydrocarbons, the molecules that make up crude oil and natural gas. And oil usually doesn't sit underground in giant empty caverns. It moves through porous rock and gets trapped in certain geological structures, more like liquid soaking into a sponge than filling up an underground lake. So oil exists. The hard part is finding where it actually collected in useful amounts. You can't drill randomly and hope for the best. A single exploration well can cost tens of millions of dollars, especially offshore. So before drilling starts, companies try to build a picture of what's hidden underground. And they do that by scanning the earth. Engineers send sound waves down into the earth or beneath the ocean floor, then measure how those signals bounce back from different rock layers. It's basically an ultrasound for the planet. From that data, computers generate 3D maps of the subsurface. Geologists then look for the kinds of structures that can trap oil and gas. But even then, nothing is guaranteed. A site can look perfect on paper and still disappoint once the drilling starts. And that's where exploration becomes a gamble. You're spending huge money based on probabilities, not certainty. To reduce that uncertainty, engineers can lower logging tools into the well to measure things like rock porosity, pressure, and how easily fluids can move through the formation. Because in oil, the difference between promising and profitable can be enormous. When oil is found offshore, the next challenge is building the system that can actually produce it. And offshore rigs are not just platforms. They're more like industrial outposts at sea, packed with cranes, pumps, pipes, power systems, living quarters, control rooms, and safety equipment, all operating far from shore in open water. In shallower areas, companies may use fixed platforms. In deeper water, they often rely on semi-submersibles, drill ships, or floating production systems. And in some cases, critical equipment sits on the seafloor itself, a subsea wellhead system that controls the connection between the reservoir below and the production system above. That means offshore drilling isn't just about reaching oil. It's about linking surface systems, seafloor hardware, and deep rock formations into one controlled chain. Then the drilling begins. A drill bit cuts down through the seabed and deeper into the rock below, and modern wells often don't stop at vertical drilling. Once they reach the target depth, engineers can steer them horizontally for thousands of feet to reach more of the reservoir from a single well. That makes production far more efficient, but it also means the real challenge is no longer just finding oil, it's controlling the well once you reach it. As drilling goes deeper, the well has to stay stable. That's why engineers line it with steel casing and seal sections with cement as they go. The goal is to isolate rock layers, protect the wellbore, and keep fluids where they're supposed to be. And the most critical protection system is the blowout preventer, or BOP. This is a massive safety device designed to shut in the well if the flow starts getting out of control. That matters because once drilling intersects a productive zone, the system has to do more than reach the oil. It has to contain it. So while the drilling process looks like a brute force operation from the outside, it's really a precision job built around control. And even when everything works, what comes out still isn't usable oil. It's usually a mixed stream of crude oil, natural gas, water, and solids like sand. So the first task at the surface is separation. Gas is pulled off, water is treated, solids are removed, and the crude is stabilized so it can be stored and transported safely. Some gas may be captured and sent into pipelines, some may be re-injected into the reservoir to help maintain pressure. And in places where the infrastructure isn't there yet, excess gas has often been burned off in flares, which helps with operations, but also raises environmental concerns. So before oil becomes fuel, it first has to be cleaned up from a messy, unstable production stream. And this doesn't just happen offshore. A huge portion of this process happens on land too, especially in the United States, where modern drilling and fracking turned regions like Texas into some of the most productive oil fields in the world. Once crude oil has been separated and stabilized, it has to move. Sometimes that means pipelines running across land or under the sea. Other times it means giant tankers carrying crude between continents. That's when oil starts moving less like a simple product and more like a global circulation system. From well to separator. From separator to storage. From storage to pipeline or ship. From there to terminals, refineries, and distribution networks. It never really stops. And this is the part most people rarely think about. Oil is not just an energy product, it is a logistics product. If one link in that chain breaks, prices can move thousands of miles away from the actual problem. A disruption in one region can affect fuel costs in another. A bottleneck at one refinery can ripple all the way down to local gas stations. And a delay in shipping crude can turn into a real cost for drivers, airlines, factories, and delivery networks. Because oil does not just power machines. It moves through a machine of its own. And after all that effort, crude oil is still not the finished product. It still has to be transformed. When crude arrives at a refinery, it enters one of the most complex industrial systems on Earth. The first major step is heating it and sending it into a distillation tower. Inside that tower, hydrocarbons separate based on boiling point. Heavier fractions stay lower, lighter ones rise higher. That first split produces streams that can become gasoline, diesel, jet fuel, lubricants, and petrochemical feedstocks. But refineries don't just separate crude, they also reshape it. Heavy molecules can be cracked into lighter ones. Other streams can be reformed to improve fuel quality. Then everything is blended to meet exact performance standards for engines, emissions, and storage. So the refinery is not just sorting oil, it's turning a raw geological material into usable modern fuels. And that means the gasoline going into a car is the final result of an incredibly long chain. Ancient organic matter, burial, heat, and time, seismic imaging, drilling, well control, separation, pipelines and tankers, refining, distribution. All so somebody can stop for 5 minutes, fill a tank, and drive away. Oil helped build the modern transportation system. It supported industrial growth. It made large-scale logistics, aviation, and global trade possible. But the trade-offs are real too. Oil extraction and transport can cause spills and local environmental damage. Burning petroleum products adds massive carbon emissions to the atmosphere. And because so much of the world still depends on oil, supply disruptions can trigger economic shocks far beyond the energy sector. So the story of oil is not simply good or bad. It's the story of a resource that made modern life possible, while also creating long-term environmental, political, and economic consequences the world is still trying to manage. And that's why oil remains such a powerful topic. Oil didn't just build the modern world, it locked the modern world into a system that's incredibly hard to change. Because replacing oil is not just about replacing gasoline. It means replacing the fuel in planes, the feedstock in plastics, the energy behind shipping, the chemistry behind everyday products, and the infrastructure built over more than a century. So here's the bigger question. As cleaner energy systems grow, which part of oil do you think will be hardest to replace first? Transportation fuel, petrochemicals, aviation, or heavy industry? Let me know in the comments.